Well, thank you very much for that introduction, Randy. It's my pleasure to be here and to present a little bit of the things that I've been working on this summer for my Hollings Scholar internship with Central Region STI. But the title that we've given to my project is NBM Performance Across Central Region. I look at seasonal verification and high impact events. And as Randy said, I've looked at two different types of things here, the seasonal verification, which we'll look at first, and then high impact weather events, how the NBM performs in high impact weather events such as high heat, heavy precipitation, and high winds. But first, just a little about me. So I'm an Indiana native, grew up in West Lafayette, Indiana, right where Purdue University is located. I'm currently a senior at Purdue University studying atmospheric science and Spanish. I'm dual majoring in those two. I love weather, as many of you probably have that same passion. I love weather. All these pictures that I've taken here, I've taken myself. The bottom right is a picture I took on a storm chase out in Iowa. And then the bottom left is a fire, actually, not too far from my parents' home my grandparents' home, I should say, on Traverse Mountain in Utah. I love basketball. Purdue basketball is one of the things I love about Purdue. I'm a ham radio operator as well, and I'm also, as obviously the reason why I'm talking here is that I'm a Hollings scholar. So. But now let's jump into the project. So this as has already been stated, we've looked at two different things here. Bulk verification statistics were conducted on NBM version 3.2 and version 4.0 to determine the average improvement between the two versions to see how much the version 4.0 has improved. The NBM forecasts for extreme weather events, including heat waves, heavy rain, and heavy winds were recorded and later compared to observations. So first, we'll take a look at the NBM bulk verification. But before we get into that, here's a poll everywhere question. And as Randy said, there's the information is up at the top. But with respect to wind speed, which of the following data sets does the NBM bias correct to? And we'll talk a little bit about this after we've answered this question. I'll give you a few more seconds here. So it looks like there's a pretty good consensus, both Irma and METARs. And yeah, that would be correct. So we'll go on, I think. Okay, here we go. So background information on the bias correction, NBM bias correction, and this is just the next few slides here before we get into the meat of what I've been doing. But the NBM bias corrects to Irma using the past 60 days, and the weighting has changed slightly from version 3.2. In the summer, more weight is given to the past 10 days, and you can see that to the right. In the NBM version 4.0, which was implemented in September 2020, an additional bias correction was added specifically for ASOS and AWOS sites. And why is that? Well, because winds in the Irma are often too light versus METARs. This problem is caused by incorporating the incorporation of mesonets, especially CWAP, AWS, and crowdsourced mesonets.
Hey, Jonathan. It appears we're having an audio issue here.
Oh.
I'm getting comments.
You guys not hear me?
Cannot hear you.
Can you hear me?
I can hear you. Oh, we're gonna have to go back to the top. Sorry.
Oh, did no one hear me at all?
No. Okay. Sorry, everyone, for the audio issue there. Welcome to the Wednesday guest speaker series. This is Randy at Central Region headquarters. That was my error. So today we have Jonathan DeGraw speaking from Purdue University. He is our Hollings scholar that's been working with us virtually this summer. And he's been looking at NBM performance across Central Region, both from a seasonal verification standpoint and high impact events. So we're going to have him kind of go over his findings from the summer. He's looked at a ton of NBM data, not just in Central Region as well, but also in other parts of the country. But we're going to be using Poll Everywhere. As you'll see at the bottom, you can go to pollev.com, rgram 936, or you can text rgram 936 to 22333 when we get to the Poll Everywhere slides, and that information will appear on the Poll Everywhere slide. So I think Jonathan's got a lot of great material to share today. He's done an absolute ton of work looking at NBM this year. And Jonathan, thanks very much for putting this presentation together and joining us today. As I said that when we first kicked it off a few minutes ago, the floor is yours.
Okay, it's all working now, right? You all can hear me?
Yes, I'm getting affirmatives.
Okay, good. Okay, that's pretty funny. Okay, thank you, Randy, and it's my pleasure to be here. It's been a great this summer working with Central Region STI. I've loved it, and despite the fact that it's virtual, but it's worked out well, and I feel like I've learned a little bit. So it's my pleasure to present what I've been working on this summer. But right here you can see the title of my project, the NBM performance across Central Region, a look at seasonal verification and high impact events. And so this presentation will be split in two. We'll first talk about bulk verification of the NBM, and then we'll talk about different events that have occurred during the summer where we've looked at the performance of the NBM in those specific situations. But first, a little about me. I'm an Indiana native, so grew up in West Lafayette, Indiana, actually, which is right where Purdue is located. Go to Purdue. I'm a senior, currently studying atmospheric science and Spanish, dual majoring in those two. I love weather. I'm an avid weather enthusiast. You can see these pictures here I've taken. So you have some, fair weather cumulus, and you also have some. The bottom right is a picture I took in Iowa on a storm chase. And then the bottom left is a fire that started not too far from my grandparents' home on Traverse Mountain in Utah. Anyways, but I love basketball too. Purdue basketball is awesome, despite the fact that they sometimes disappoint me. But I love Purdue basketball. And as has already been mentioned, I'm a Hollings scholar, so that's just a little bit about me. Getting into the project now. So as I said, I've split it into two. Bulk verification statistics were conducted on the NBM version 3.2 and version 4.0 to determine the average improvement between the two versions. And then the second part is we looked at NBM forecasts for extreme weather events, including heat waves, heavy rain, and high winds. And we later compared that to the observations. So first, looking at the NBM verification. And so we already kind of saw this, but I guess we'll go through this poll everywhere again. I'll wait for just a few minutes, but the question is, with respect to wind speed, which of the following data sets does the NBM bias correct to? With respect to wind speed. So looks like we got some Irma and METARs. So, well, we'll talk about this a little later, but both Irma and METARs, it bias corrects depending on where it is in we'll talk about it more in the upcoming slides, but thank you for participating, by the way. So background information on the bias correction of the NBM. So the NBM bias corrects to Irma using the past 60 days. And the weighting has changed slightly from version 3.2 to version 4.0. And in the summer, more weight is given to the past 10 days. And you can see that in the right. But it also, additional bias correction in the 4.0 is given specifically to ASOS and AWAS sites. And why is that? Well, IRMA, often winds at in IRMA are often too light versus METARs. And this problem is caused by the incorporation of mesonet winds such as CWUP, AWS, and cross-source mesonets. So that's the reason why both of them are used. So a little background on the IRMA. So IRMA analysis begins at a 50-50 blend of the HER and NAM nest. An initial IRMA analysis is nudged towards observations in MADIS, so the ASOS, AWAS, mesonets, etc. And an automated quality control does take place to help filter out bad observations. With the version 2.8 upgrade in July 2020, wind observations are adjusted based on provider, which is useful since prior to that, all observations were assumed to be 10 meters above ground level, which is not always true. And then I have a little link. We'll probably send out this this PowerPoint presentation, this slide deck. But there's a link here so you can see how the IRMA is matching observations. So the stations used so there's two different types of verification you can do per the NDFD viewer verification site. One of them is station verification, and there are more than 500 stations used in station verification, and I've shown those to the right. For the NBM version 4.0, METAR observations recorded at these sites are now implemented in the bias correction. So in the bias correction, for each IRMA grid point, NBM checks if the METAR observation exists, and if it does, that value is replaced. The METAR grid value is replaced, grid point value is replaced by the METAR value. And then that modified IRMA is used in the bias correction. And then you'll note, this is just a note, the figures to the right show NBM MAE for each station, and the later figures, all that will be aggregated, it will be smoothed out. So that's just a note for these later slides that I'm about to show. So methodology, as I mentioned, we used the NDFD verification viewer to retrieve the data. So we looked at mean average error, MAE, and bias correction, bias verification data for NBM. We looked at two sets, March through May 2020, which is version 3.2, and March through May 2021, which is version 4.0. And so why do we pick this time frame? Well, the NBM version 3.2 was implemented in February 2020, and NBM version 4.0 was implemented in September 2020. So March through May are the only months where we have the two version overlap. I guess March through June now, but back when I was doing this, all these crunching these numbers, doing these both statistics, we didn't have the June monthly data yet, so we only used March through May. And it should be important to note that March through May is a volatile time for bias correction, since there are rapid pattern changes in synoptic weather. So as a result, improvement or degradation in the NBM may be attributed to a volatile bias correction and not necessarily to changes in the NBM. And we'll see that kind of especially in the temperature forecasts. For the NBM, so only NBM forecasts issued at 19Z were used for wind speed and wind gust verification, and for max and min temperature verification, all available NBM forecasts were used. And then I would like to give a special thanks to Dennis Strom. I emailed him at the beginning when I was starting the bulk statistics, and he provided me with some initial data sets in bulk, which was very useful. So thanks to him. And then for the subregions, so we looked at the entire central region as a whole, and then we looked at each subregion as well. And the data for each, so for the subregions, we collected all the data for each WFO, we aggregated it using a case-weighted average, and then we generated figures. And in addition to these figures that I'm about to show, we also looked at the average improvement and also the average bias for version 3.2 and version 4.0. So, and before I get into the results here, this is just a figure of the subregions, just as a reminder. So we'll be looking at each of these subregions in a minute here. So wind speed, I'm going to try to go through these quickly because they're pretty much the same slide, just with different weather parameters. But So for the central region, you can see that the improvement from version 3.2 to version 4.0 is noticeable. MAE is less than version 3.2 at all forecast projections. And note the improvement in the extended range. We'll see this in a lot of the wind parameter slides. Average improvement from the version 3.2 to version 4.0 is 17.41%. And all the subregions had are experienced an average improvement above 10%. And the most improved, as we'll see in this next slide, was the upper Mississippi River. And so you can see, look, notice the improvement in all of the subregions. There was an improvement in the extended range, which is an interesting feature of this verification. Looking at station verification, you can see that the magnitude of MAE for both version 3.2 and version 4.0 is greater. This is true for all, or greater than IRMA verification, I should say. And this is true for all wind forecasts. So you'll see this in later slides as well. Version 3.2 and version 4.0, or the difference between the two, is greater in station verification than IRMA verification, meaning that the margin of improvement is greater. And then the average improvement between the two versions is 23%. All subregions experienced an average improvement above 14%, and the most improved was the Central Plains region, as we'll see here. And so this is just the improved, or the station verification for each subregion. Once again, the Central Plains is the most improved of all of the subregions. And you can see that the margin, as I said, the margin improvement is on average greater than in the IRMA verification. You can also see that in these percents here. So the bias now, we're looking at the bias. You can see for both version 3.2 and version 4.0, there's a slight negative bias. The version 4.0 is less biased on average than version 3.2, or at most forecast projections. And once again, note the improvement in the extended range. For central region, the average bias was version 3.2, for version 3.2 was negative 1.68 knots. And the average bias for version 4.0 is negative 0.67 knots. So just a slight negative bias. And once again, note the improvement in the extended range, and the Central Plains region was the most improved in regards to bias. You can see that there was the biggest jump in improvement in the Central Plains region, subregion. So looking at station verification now, the magnitude of bias is much greater in station verification than IRMA verification, as has already been mentioned. You can see that the difference between the version 3.2 bias and version 4.0 bias in the station verification is noticeable, and version 4.0 is less biased on average than version 3.2. And you can see that overall, the average bias in version 3.2 is negative 4.41 knots, and the average bias in version 4 is about negative 3 knots. So, and then just to look real quick once again at the subregions. The Southeast was the most improved for bias for wind speed. So now looking at wind gusts, you can see that the chart looks similar to wind speed, but a little different. And we'll see that there's a large difference between IRMA verification and station verification in this case. But you can see once again that the MAE is in version 4.0 is less than version 3.2 at all forecast projections, denoting that there was a significant improvement. You can see the average improvement was 29.37%, and all subregions experienced an average improvement above 20%. And you'll see that the highest, or the most improved, with the Southeast with 39% improvement, which is pretty good improvement. Once again, note the improvement in the extended range. This seems to be a feature in the IRMA verification for most of this, for most MAE in the for IRMA verification. So looking at the station verification, you can see that the improvement is not as great. The average improvement is only 10.29%. The magnitude of improvement is less, definitely, than the station or IRMA verification. And all subregions in the central region improved, but there were a few that only improved by about 1%. So, the station verification doesn't show as high of an improvement. Central Plains region had the greatest amount of improvement of all the subregions. Looking at the bias, the wind gust forecasts have a negative bias once again, or the magnitude of version 3.2 increases significantly with forecast projection for version 3.2, while the version 4.0 doesn't seem to increase as much, so there isn't as much bias once again in the extended range. And then average bias for version 3.2 is about negative 5 knots, and the average bias in version 4.0 is about negative 2 knots. The most improved of all the subregions was the Central Plains region in this case, and you can once again see that feature, that improvement in the extended range. Looking at the station verification, you can see that the improvement is not as stark as in the biases. It's not as stark as in the IRMA verification. You can see the average bias for version 3.2 is negative 7.94 knots, and the average bias in version 4.0 is negative 7.2 knots. So less than a knot of improvement there. And we can see in the next slide here, funny enough, so Southeast region doesn't have you can see it doesn't have a lot of data. So take this with a grain of salt. But the most improved was the Southeast region in this case. And then you can see some interesting features here. You see, look, the Rockies is an interesting, interesting pattern there. But anyway, so you can see that the different that's one of the reasons why I did this, because the different subregions have different, features. It's interesting to see how it changes with regards to the geographical features in the region. And obviously, wind is definitely influenced by that. So it's interesting to see, the compare between the subregions and then the overall central region. So now we're going through temperature. Not a ton of interesting things to note here. I'll just make a note on the amount of improvement or degradation in some cases. So average improvement for version 3.2 to version 4.0 is 5.97%. In this case, this is for max temperature. The most improved was Central Plains. You can see that, but you can see that some of these subregions didn't improve at all. And you can see here the upper Mississippi Valley got worse, and the Great Lakes got worse. So for station verification, the average improvement was only about 2%. You can see once again here, the Central Plains was once again the most improved in this case. This is for bias. You can see there's a slight positive bias in both version 3.2 and version 4.0. This is IRMA verification. And you can see that it doesn't look like there's a ton of improvement. The version 3.2 bias is 0.96 degrees Fahrenheit, and the average bias in version 4.0 is 0.71. So not a ton of improvement there. The most improved was the upper Mississippi River subregion, but you can see there's not much improvement here. It looks about the same between the two versions. This is max temperature bias here. For station verification, you can see it's changed slightly. The version 3.2 has a slight negative bias before forecast hour 96 and a slight positive bias thereafter. And then version 4.0 has a slight negative bias at all forecast hours. And the average bias at the bottom, you can see average bias for version 3.2 is 0.19 degrees Fahrenheit. And then the average bias in version 4.0 is negative 0.31. So one of them is more negatively biased on average. One of them is more, positive bias on average. And you can see that the one that's less biased on average is version 3.2 in this case. The most improved, which is the upper, you can tell in the graph here, the most improved would be the upper Mississippi River subregion. And there's not really much else to say for that one. For min temperature, the average improvement was a little more noticeable, 10% on average in the central region. And most subregions did experience an overall improvement in accuracy. There was one, however, that did not, the Great Lakes. You can see that here in the graph. But most of them did experience an improvement. For station verification, the improvement, it's no longer improvement. So that's an interesting, there's quite a big difference between station verification and IRMA verification. But for station verification, the average improvement was actually negative 1.62%. So showing that it's a slight, slight decrease in the accuracy of the min temperature forecasts. You can see that the only one that had a significant improvement in the accuracy was the upper Mississippi River subregion, and many of them had a slight decrease in accuracy. So for the bias for min temperature IRMA verification, you can see that both have a slight positive bias. The bias in version 3.2 is 0.47, and the bias in version 4.0 is 0.61 degrees Fahrenheit. And in version 4.0 is more biased than version 3.2 at all subregions except the North Plains region. So it seems that it got more biased, so a decrease in accuracy there between the version 3.2 and version 4.0, or a decrease, or it's more biased. And then station verification, you can see that the average bias is 0.44 degrees. In version 3.2 and an average bias in version 4.0 of 0.27 degrees Fahrenheit. So you can see that the station verification shows it less biased. And the most improved in this case was the Rockies. And you can see that on average there was an improvement. However, there are some regions that do not show much of an improvement in the bias. So that's a lot of slides, but summary conclusion here. In the central region, at the very least, the NBM version 4.0 was found to have significantly more accurate wind speed and wind gust forecasts than the version 3.2. So it had lower MAE, lower magnitude of bias on average. And this is especially true in the extended forecast range for IRMA verification. And it should be noted, right, that the IRMA verification, we saw this, the IRMA verification and the station verification sometimes disagree on the magnitude of improvement, but it does show improvement in both IRMA and station verification. However, they have a slightly more accurate max and min temperature forecast than version 3.2, but not a significant amount. You could see that it looked as if it did improve version 4.0 from version 3.2, but not by much. Lower MAE and lower magnitude of bias on average, but the improvement was not always shown in both versions. And just a note, it's important to note that NBM will continue evolving. It'll continue improving. As improvements are done to modeling, as ensembles in IRMA, as technology and post-processing advancements are made, and as the forecasters give feedback. So this isn't the end. The NBM will continue to improve as we go on to the newer versions in the future. So now we'll take a look at the second portion of the project, which is the NBM performance during extreme weather events. So we'll be looking at different events that have happened this summer that are a little on the extreme side, and we'll look at how the NBM performed during those specific events. So not just overall on the on all of the bulk through March through May, March through May, but looking at it the specific events. So we're gonna first we'll start here. So the current perception of the NBM is that it underperforms in extreme events, and as a result, does not accurately communicate the magnitude of these events. So the goal of this part of the project is to prove or disprove the validity of this claim. Obviously, looking at a minimal number of events, you can't really make a concrete conclusion. So take what we talk about here with a grain of salt. But here we'll be looking at heat waves. Unfortunately, we did not have time to do a fire weather event, so that was the goal, but I won't be sharing anything for fire weather here. But we did look at heat waves, heavy rain, and high wind. So these are a few of the tools that I've used here. Well, you'll see many of these. And I was a little curious, so I added this question here. Which of the following, this is a poll everywhere question, which of the following NBM forecast tools have you found most useful? So I've become familiar with these during the summer, but I'm curious to see which ones you guys have used the most. or which ones you found most useful? So it looks like we've got some votes for the NBM 1D viewer and the What's Up viewer. You'll see many of those, of the products used, of those products used in the upcoming slides. One of the things that I really like is the weather in context, because so obviously in this project, right, I was trying to look at if an extreme event was going to happen or not, so that I had enough time to look at all these products. And the weather in context tool, I mean, it shows well if the NBM thinks there's going to be a record event. So for me, for this project at least, the weather in context tool is pretty useful. And now they've integrated that into the What's Up viewer, so that's pretty awesome. At the beginning of this project, it wasn't in the What's Up viewer, so. Okay, well, we'll move on. So the first event we're going to be looking at is the Pacific Northwest heat event. A lot of stuff has already been done on this, actually. I've been to a few presentations where they've talked about the NBM performance in this heat event, but thought I'd put my 2 cents in there and show what I've done. So several all-time records were broken in Washington and Oregon, as probably all of you know, from June 26th to June 30th, and you can see that in the black X's in the graphic to the right. The NBM, and I put in the European ensemble here because this is taken from a different slide deck, but they did an excellent job of forecasting the event. Beforehand, the NBM forecast 100-degree temperatures in the region as early as June 18th. So it's pretty far in advance. And we'll look into that in just a minute here. So the NBM timing, the timing per the deterministic NBM, this is the forecast taken at 19Z on June 25th, shows that the 100-degree heat begins on Saturday in Western Washington and Western Oregon, intensifies into Sunday into Monday, and then the heat moves into Central Washington and Northern Oregon on Tuesday. And then the heat remains for the remainder of the week and is forecast in this case to last until Monday. So the NBM was forecasting the heat to, 100-degree heat to last until Monday, July 6th. We know that did not happen, but that was what, at least, a few days prior, June 25th, that's what the NBM thought was going to happen. Here I have the 2 sites located here. We're going to be looking at point forecasts for these 2 sites. This is OMAC, and then I would butcher the pronunciation of this. It's Wantachi. Hopefully I pronounced that correctly, but we'll be looking at these two point forecasts here. So first we'll look at OMAC. This is just a look. So prior to this heat event, the all-time record was 110 for both the record and for the month, all-time record and for the month of June, was 110 degrees, set on June 28th, 2015. Climatological normal was between 82 and 85. And it should be noted that there's only 23 years of max T data at OMAC, so take that into consideration when we're talking about these records here. But here's some temperatures recorded at this location during this heat event. So 101 on July. Oh, we'll start at the bottom here. So 101 on June 25th, 104 June 26th, 109 June 27th, and it just kept getting hotter until June 29th, which is 117, and 114 on June 30th. So pretty warm, to say the least. Looking at the probabilistic max temperatures that, those forecasts, the max temperature forecast, probabilistic max temperature forecast, during, the 10 days prior to this event, you can see that the observed temperature for June 29th falls above the 90th percentile at all forecast projections, at all forecast hours. So it never was within the 90th percentile, the actual temperature that occurred. The NBM does forecast a record heat event though, as early as day 7. So you can see here, you know, the mean is as greater than 110 degrees on June 24th. So there was, despite the fact that it didn't get the magnitude, the severity of the event, it still forecast well in advance a high heat event. Looking at the deterministic max temperature, you can see that it also falls below, the deterministic max temperature also falls below the observed temperature by at least 3 degrees at all forecast projections, so it never quite reaches the actual temperature. But it is forecasting, once again, a record heat event as early as June 24th here. So this is now looking specifically at the forecast for June 25th. The deterministic forecast predicts above 100-degree temperatures from June 26th through July 5th, as already mentioned, so 9 consecutive days of above 100-degree temperatures. And the 100 degrees falls below the 25th percentile from June 27th through July 1st. And you can see here, this is just a note here. Actually, I think I talk about this in the next slide. So the actual temperature, the actual temperatures fall on or above the 95th percentile from June 25th through 30th. You can see this here. These red dots are the actual temperatures, the actual max temperatures. So it falls above the 90th percentile at all for all these days, and then it's below the 25th percentile for Thursday, for July 1st. So and then the deterministic forecast is on average, there's an average of 3.2 degrees Fahrenheit below the actual temperature. So it was a little low, and then it was a little high. So so now we're going to be looking at the second point forecast. This is for Wenatchee. Hopefully I'm pronouncing that correctly, Washington. This has a little bit more longer climatological record, so that you could have a little more confidence that these records are actual records. But anyways, all-time record for here was 109 degrees, set in the same day as the other point forecast, actually, June 28th, 2015. Climatological normals between 81 degrees and 84 degrees Fahrenheit. And then you can see a list of temperatures here. I'll just make a note of the 114 degrees that also occurred on June 29th. So once again, the highest temperatures on June 29th. So looking at the max temperature, or the probabilistic max temperature forecasts, looking at how those verified. So the observed temperature for June 29th falls below, once again, the 90th percentile, but above the 75th percentile for, oh, sorry, I should reread that. So this time it did fall below the 90th percentile, but above the 75th percentile for forecast days 3 through 5. And then for days 1 through 2, the observed temperature is at or below the 75th percentile. So you can see the probabilistic forecast is a little bit better at this location than at the other locations. And you can see, or at the other location, OMAC. And you can see once again that the NBM forecast a record heat event. In this case, the record was 109 degrees. You can see that it was forecasting heat above 109 degrees as early as day 7. Once again, you can see that the mean is once again at or above 109 from June 24th on. So looking at the deterministic forecast, it didn't match, the deterministic forecast didn't match the actual observed temperature until the day of 24 hours before. So the deterministic forecast, however, did forecast a record heat event as early as day 6 as well. So looking at just the forecast for the forecast for June 25th, you can see once again these dots once again are the actual temperatures that were observed. The deterministic forecast predicts above 100-degree temperatures from June 26th through July 5th once again, so 9 consecutive days of above 100 degrees. And then 100 degrees falls below the 25th percentile for June 27th through the 30th. So once again, you can see that it was predicting a high heat event. the actual max temperatures fell on or above the 50th percentile, which is better than the previous at OMAC, from June 25th through the 30th. You can see here, max temperatures fell above the 75th percentile for June 27th and 29th. The deterministic forecast was an average of 1.2 degrees below the actual temperature, and the max temperature for July 1st fell near the 25th percentile. So once again, you can see it's significantly less than was predicted. So the deterministic forecast was 7 degrees above the actual temperature at this location as well. Oh, and just a note, these black dots are the deterministic forecast. So you have on here you have the probabilistic, the deterministic, and the actual observed value. So just a summary real quick of the heat event. So the NBM predicted a record heat event many days in advance. So the NBM forecast 100-degree temperatures in the region as early as June 18th, and the temperatures above 110 degrees as early as June 24th. The NBM deterministic and probabilistic forecasts that were initialized to June 25th at 19Z did not correctly forecast the end of the heat event on July 1st. It forecast temperatures above 100 degrees as far out as July 5th. So it didn't, the timing wasn't exactly, the timing of the ending of the event wasn't exactly well predicted by the NBM, at least at that forecast, Record highs set on June 29th were significantly higher than the NBM deterministic forecast and above the NBM probabilistic forecast 75th percentile at both locations. But here's the key takeaway. The NBM deterministic and probabilistic output did capture the extreme heat event well in advance of its occurrence. And although the deterministic output was underdone on the magnitude of the full event, the deterministic forecast in concert with the percentile data was more than sufficient to anticipate and message this event. So that was the Pacific Northwest heat event. There were other heat events that we looked at that we don't have time to go into. There's a lot of heat events this summer. But now we'll be looking at a high wind event, which is interesting because we looked at how much on average the NBM version 4.0 has improved from version 3.2. You'd see the very distinct, there is definitely an improvement in both wind speed and wind gust. But how does it do in high winds? At the very least, how did it do in this event? So we'll look at that. So this is just a look at the wind or the watches that were and warnings that were issued. This is on June 10th. So then this is just a few quotes from the products that were put out that day. So we have winds of 35 to 45 miles per hour with gusts to 60 mile per hour possible. And then it was expected to occur from Thursday afternoon into late Thursday night. So we'll see how the NBM did. Anyways. So here's some products from the What's Up viewer. This is for Thursday evening, June 23rd. And the NBM showed wind speeds ranging from 20 knots to 30 knots or from the mid 20s to mid 30s miles per hour in the watch area. Wind gusts in the watch area range from 30 knots to 40 knots or upper 30s to upper 40s miles per hour. Overall, the NBM forecast wind speeds and wind gusts less than the high wind watch suggested. Looking at some point forecasts, this is a point forecast for Laramie, Wyoming. This forecast was initialized at June 9th at 19Z. So this is the day prior. This is about 24 hours before the peak wind speed. But it was forecasting the wind speed and wind gust to occur at 21Z on Thursday. The max wind speed was to be about 25 miles per hour, and the max wind gust to be about 38 miles per hour. And the wind direction was, we're not going to look too much at the wind direction, but the forecast wind direction was approximately 200 degrees, so south-southwest. So let's see, how did it verify? So wind speeds did occur at 21Z as predicted. So the prediction was more or less correct. The observed wind speed at 21Z was 35 miles per hour, which is 10 miles per hour above the forecast. And the observed wind speed at wind gust, I should say, 21Z was 51 miles per hour, which is 13 miles per hour above the forecast. So needless to say, it was a little bit above what the NBM was saying it would be. And here's some observations. So at Laramie, so the max wind speed per the climatological summary was 40 miles per hour, and the max wind gust was 55 miles per hour. And the time of the max wind speed was approximately 4 o'clock Mountain Daylight Time, which is about 20 Z. So the timing was more or less correct, but the magnitude of the event was not. Very, very significantly lower than the actual magnitude of the event. Here's we'll just quickly go through these. The things that I think is most interesting about these slides here, is the bias correction. So you can see in this one there's a larger distribution in raw values of the NBM members and the bias corrected values. There's a large distribution in the raw values, I should say. So you can see that here, large distribution in the raw. The bias correction makes it converge a little bit on one it makes the distribution smaller. But you can see that the opposite is true for the wind gusts. So I thought that was interesting. I threw that in here. These violin plots are interesting to look at in terms of looking at how the bias correction affects the NBM. But a summary, just real quickly, the NBM wind speed and wind gust forecasts were significantly lower than the realized values, but the timing was more or less close. So 21Z versus 20Z, and so more or less the same. But so the timing was correct, but the magnitude was not. So we've looked at high winds, we've looked at high heat. Now we're going to look at a heavy precipitation event in the Midwest from June 25th through June 26th. And well, there was a lot of rain that end of the month out, in the Missouri area, out in the Midwest. So we'll be looking at this heavy precipitation event in the Midwest here. So before we get into that event, just a quick question here. For QPF, what is the NBM deterministic forecast? This was changed recently, so I thought I'd throw this in here. Well, we'll review this in just a minute, but I'll let everyone answer. I'll give a few seconds for answers. Okay, so it looks like, yeah, everyone's got it correct. It is the average of the gem and the 50th percentile. So we'll move on here. It's just a real quick review of this. I'm not going to read through this, but it talks about how the probabilistic is calculated. But as you can see here, as of March 2021, so as I said, relatively new, this change. The NBM deterministic QPF is the average of the gem and the 50th percentile. And so this approach, note that this approach causes the deterministic QPF to fall usually between the 50th and the 75th percentile of the NBM ensemble distribution. Okay, so let's get into the event. So this is on June 23rd. So what is this, 3 days before? Yep, day 3. 3 days before the event. And you can see that the WPC has put out an outlook for excessive rain in Illinois and Indiana. I have a little quote here from their discussion, but it says model spread continues through Friday, but there is enough multi-model signal to highlight the potential for robust rain rates over modest flash flood guidance. And so we're going to look at that here in a minute. The NBM was showing a pretty strong signal in that area, but you can see that it changed in the day. This is the day prior. This shouldn't say day 3. This should say day 1. But it's this is the forecast the day prior. So the rain shifted, or the WPC shifted their outlook for the heaviest rain to be further south than the previous forecast or the previous outlooks. Yeah, and notice how the higher confidence is now in Missouri. So it's no longer where it was up here, but it's now in Missouri for both days. And so we'll see that reflected in the NBM as well. But so this is the NBM. This is initialized 0Z on June 22nd. You can see it has the rain coming in from Iowa, moving into Illinois and Indiana. And the highest rain rates appear to occur up here in northern Illinois between 6Z and 12Z on June 25th, or up here, so southeast Illinois, southeast Iowa, northeast Illinois. And then the rain moves through on the 26th. So here's an updated, this is a day prior to the event, so 0Z on June 25th. So this one shows, obviously you can see there's a very big difference in between these two forecasts. You can see that it's no longer forecasting all of this rain up here, but you can see it was forecasting the rain down here, the highest rain right here in Missouri. So I'll just read through this real quick. Shows the highest rain rate early Friday associated with the MCS in northeast Missouri, and then the MCS moves southeastward into southern Illinois by 12Z. And then rain occurs again in northeast Missouri on Friday into Saturday. I think I'll just skip this slide actually. But so looking at a point forecast. So the initial forecast on June 23rd was showing it to be in northern Illinois. So we are going to look first at a point forecast in Rockford, which is in northern Illinois. So the NBM forecast for Friday, this is initialized on June 21st at 19Z. The 12-hour pop shows an 81% that 81% of the ensemble members are reporting measurable precip between 12Z Friday and 0Z Saturday. So pretty high confidence that there will be rain in this area. 24-hour probabilistic forecast shows 0.43 inches, 0.97 inches, and 1.54 inches as the 25th, 50th, and 75th percentiles respectively. And the ensemble mean is 1.66 inches. And then the 48% of the ensemble members that report measurable precip also report precip above 1 inch. So, I mean, that's pretty high confidence there will be a decent amount of rainfall here in Rockford, according to this forecast initialized on June 21st. So then we look at the updated forecast, this is taken, I believe this was taken 0Z on the 25th. Sorry, this is incorrect. I believe this forecast was taken 0Z on June 25th. But anyways, the 12-hour pop shows once again a high confidence in measurable precip. 91% of the members are reporting measurable precip. You can see the probabilistic forecast shows 0.4 inches, 0.85 inches, and 1.4 inches as the 25th, 50th, and 75th percentiles respectively. And the mean and the ensemble mean is 1.42 inches. And then 42% of the ensemble members that report measurable precip also report precip greater than 1 inch. So it's pretty high confidence still that there's going to be a decent amount of rainfall. But we can see that didn't quite happen. Rockford is up here. I should have labeled that, but Rockford is up here. But the highest rainfall rates occurred out, in the Rock area. They occurred out near Kansas City here, a little farther north, I guess, of Kansas City. But as it says here, rainfall was recorded from northeast Missouri into central Missouri, and some stations recorded values as high as 10 inches. So there's some pretty high rainfall rates, accumulated rainfall, pretty high rainfall. Some high values were also recorded in Illinois, a little bit, southeast of where Rockford is, or southwest, I should say. But a few, in this spot here, a few stations measured values greater than 4 inches. And then, so this is the second day. We didn't look at forecasts for this day, but there was, still the next day, there was still a lot of rainfall. You can see that the highest rainfall was reported in central southwestern Kansas. Several stations reported values greater than 6 inches. And some high values were also recorded in Missouri and Illinois. A few stations measured values greater than 4 inches at Jefferson City, which I believe is here. And several stations measured values greater than 5 inches in Bloomington out here. So how did the NBM do? Well, the forecast initialized on June 25th. For that forecast, the actual QPE was well below the 25th percentile, and the deterministic the QPF was significantly above, 1.57 inches above the actual amount. And then for the forecast initialized on June 25th, the actual QPE was well above the 10th percentile QPF, and the deterministic QPF was 1.31 inches above the actual amount. So even a day prior, it was still, suggesting much more rain at Rockford, Illinois than actually occurred. So what does this say? What does this tell us? Well, both the NBM and we didn't look at the European here, but the European also did this. Both of them correctly forecast a high precipitation event on Friday. However, even 4 days out, they did not predict the location of the rainfall correctly. And this suggests that model inputs to the NBM have trouble accurately predicting mesoscale features, including convective precipitation, as was in this case. So, conclusions for this part of the project. We looked at high heat event, a high heat event, a high wind event, and a heavy precipitation event. Firstly, sweeping conclusions can't be made based on a minimal number of cases. So these are just some, observations here. But we can't make any sweeping conclusions. But it appears that the NBM has skill in forecasting high heat events. And this is not only true for the Pacific Northwest heat event. I have here a link to another one of my presentations that I did on a different high heat event in the High Plains. But it's the ridges are a little bit easier to forecast. And so for that reason, probably it's the NBM can forecast these events, high heat events, days in advance. The NBM, it appears that the NBM doesn't have much skill in forecasting high wind events still. While the accuracy in the NBM version 4.0 wind speed and wind gust forecast has increased significantly from version 3.2, still has trouble, as shown in this event, still has trouble forecasting those high winds. It got the timing right, the timing of the highest wind, but the magnitude of the wind was still not correct. And then the NBM has some skill predicting heavy precipitation, but it has trouble predicting mesoscale features and events, which is understandable. And but it can accurately predict, different, synoptic weather events and timing. So that's been my project this summer. It's a lot of information, but I hope you've enjoyed it. I've definitely enjoyed working here with Randy and Andy and Bruce at the Central Region STI. And I'll open it up to questions if you have any questions for me.